This is a video about free body diagrams. We'll be solving force problems for some time. It's always a good idea to have a game plan. With kinematics, we made a table of values, and we had our three kinematic equations, which made for a good consistent starting point. Now we'd like to have something like this for forces, and this is where free body diagrams come in. A free body diagram shows all the forces acting on a system. So far the only forces we've discussed are the normal force, tension, and gravity, so I'm going to make a couple of free body diagrams using these. While it's not necessary, I personally also find it helpful to include an axis or a set of axes in a free body diagram. So for the first one, let's do a wrecking ball hanging on a cable. I'm going to represent the ball with a dot. Acting on this, I have a force from gravity. I also have this cable attached to the top, so I have a tension force pointing upward, and those are all the forces that I have acting on this ball. I'm going to put in an axis and say that upward is going to count as my positive y-axis. I like to put my axis in a different color, and that would be my free body diagram for that. Easy one. Next up, we'll do a person pushing a block on a horizontal floor. So, horizontal floor, put our block, and we'll have someone pushing this. So I'm going to draw a free body diagram for the block. I will represent the block with a dot. Pretty standard. And then draw the forces acting on it. The block has mass. If it has mass, then it gets a force from gravity. It's sitting on the ground. Back here, this wrecking ball wasn't sitting on the ground at all. It was just hanging in space. Now, this is sitting on the ground, so the ground is going to exert a force back upward against it. And because it exerts that force perpendicular to itself, that's going to be called a normal force. The person is pushing to the right, so we're going to get a force to the right. Now, we can call that a push force, we can call it an applied force. Because you're pushing against the surface, it's also a normal force. I've already used N up here, so I'm going to just give it P for push and call that good. For an axis, I'm going to say, let's have this be my x-axis. And I've got vertical forces too, so I will have that be my y-axis. There's that part, and I have my free body diagram. Let's do another. I'm going to do a block sitting on a ramp. Okay, this is where things get a little bit less intuitive. They shouldn't, but they do. Here is my block, and I'm going to draw kind of a dotted line for where that ramp is. So the force is acting on this thing. It has weight, or it has mass, so it has weight. There's mg. It has a normal force, which has to point perpendicular to the surface. So it's going to point this way, so that this makes a right angle with my ramp. That's my normal force. A lot of times people see a block on a ramp and they want to put some kind of a force going down this way. It's not there. The only reason this thing moves down the ramp is because of this combination of this gravity force and this normal force. When I am setting up my axis for this, I'm going to recognize this block is going to move along the ramp. So I would actually like to take my x-axis and have it move along the ramp. That way my motion is going to be in just the x direction. It's not going to be, right, if I did my normal motion like this, then when the box moves this way down the ramp, it would have an x component and a y component. That's a lot more work to solve mathematically. So I'm going to make my x-axis along the direction of motion, and then my y-axis is just perpendicular to that. And there is my free body diagram. I'm going to do one more. Here's a block. Here's another block. And I'm going to have a person pushing on this. Call this thing block 1, this thing block 2. A free body diagram for block 1 is going to look like this. I've got gravity. I pretty much always will have that. There is the floor. So I've got this upward force. I've got the person pushing. And I also have block 2 sitting against block 1. So this is the force from block 2 on block 1. It's perpendicular to a surface, so it is a normal force. I'm going to call this force on 2 from 1. The only reason I'm not calling it N for normal force is that I've already got an N up here, and I'd like to be able to just have different letters for my forces if I can. The box is going to move horizontally, so it makes sense for that to be my x-axis. Y is perpendicular to it. That's my free body diagram for block 1. Block 2, I've got my dot. I've got mg going downward. It's sitting on the ground, so I've got a normal force going upward. The person is not pushing on block 2. The person's pushing on block 1, which is pushing on block 2, but the person's not in contact with block 2, so this push force won't be there for block 2. However, block 1 is pushing block 2 to the right, so I'm going to get a force like this to the right. That is the force from 1 on 2. I'm going to draw my axis. My motion is still horizontal, so I'm going to stick with an x-axis that's horizontal. Y-axis has to be perpendicular to that. Vertical is nice. And I get a free body diagram for block 2. I do want to point out one thing. This force right here, the force of 2 on 1 and the force of 1 on 2, these make up a third law pair, so these will be equal and opposite to each other. That's something that we'll talk about in a future video too. So these are all examples of free body diagrams. For now, there's not much that we've done with them, but it's a starting point. Using free body diagrams to solve problems, that's a subject for another video. For right now, this is where we are.